the coolest feature we learned I guess the coolest thing I've learned right now is I'm just music is the is else those are cool. Yeah.
So I want to just recap what we did last time. Not everything, but a little bit of what we did last time. So, right? Does everyone remember what we did? Entropy, right? We talked about entropy and how to calculate it. And we started from here. We said for basically an equilibrium process. ds, which is the symbol for S is the symbol for entropy, is dq over t. Okay? And so that's how you would calculate it. And the second law says the entropy for a closed system or for the whole universe, it's always either constant or greater or equal to 0. So the equality is if you have a process that is reversible, then you have delta S is equal to 0. And if it's irreversible, then it would be greater than 0. And we made a few calculations. So for example, the entropy of heating, right? So we said, for example, if you have let's say you have ice at 0 degrees, right? Ice at 0 degrees. And let's say you have 100 grams of ice at 0 degrees. And that ice, we will add heat to it until the ice melts and becomes water at 0 degrees. Of course, it's still 100 grams, right? So, what's the change in entropy in this case? Well, notice it is ice at 0 and then it's water at 0. So, has the temperature changed?
No.
No, the temperature has not. Thank you. And so, what is the change in entropy? We start from here. So, delta S is you integrate ds, and that's equal to the integral of dq over t. And since the temperature is constant, you can move 1 over t outside. And then dq here, the integral will be the amount of heat that you have added. The amount of heat. And I will set q over t. Let's just put it here. Q over t. Now, how much is Q? Well, Q is the amount of heat that you have added, right? Q would be the amount of heat that you have added. And so, for example, in here, Q that you have to add will be the mass of the ice, right? The mass times the latent heat. And so, 0.1 for the mass, and the latent heat is a number that is given to you, or you look it up. In a quiz, of course, I will give it to you, because you cannot look it up. So, it turns out it's 333 times 10 to the, I think, 3. Okay, so it's 333 times 10 to the 3. If I'm wrong, please correct me, but I'm doing it from memory. It sounds right? I think it's right. Because I think if you move the decimal, it's 3.33 times 10 to the 5th, and I think I'm sure about that. Anyways, so you get, it becomes 333 times 10 to the 2. Times 10 to the 2, right? Because 0.1. And so, that's the heat that you have to add. And therefore, the change in entropy in this process is Q over T. Q over T. So you got 333, I'll put 0, 0 here for the 100 times 10 to the 2. Now the temperature, if you try to plug it in degrees Celsius, you will have to divide by 0, right? That's not good. So it's not in degrees Celsius, the temperature is in K. And 0 C is 273, right? So 273, and if you have a calculator, please help me with this. joules per Kelvin. 121?
121.1.
Okay, 121. Okay, sounds good. Yeah.
For something similar to
Sorry,
this,
121.9.
So 2?
Yeah.
Okay, sounds good. Thank you.
So if we have a scenario, something similar to this, but temperature is not constant.
Yeah, so that's the next part.
Okay,
So,
okay.
yeah, so now let's take this, and I'm going to heat it to 50, right, just 50, whatever, so the temperature will change. So now let's say I go, so this is another example, so let's say I have now water at 0 degrees Celsius, and it's still 100 grams, right, 100 grams, and it becomes water at 50 degrees Celsius, and it is, of course, it's the same 100 grams we're heated to 50. And the question now is, what is the change in entropy? So we have delta S. Let's raise this one a little bit so I can write. We have delta S equals to the integral of d cubed over t. So now, do I know how much q I have to add? The answer is yes. Yeah, we can calculate q that we have to add to warm it up from 0 to this. But what is dq? Well, remember, yeah, let me maybe be detailed. I wasn't as detailed last time. So delta q, or the amount of heat that you have to add, is the mass times the specific heat, right, of water, and then times delta T. And delta T is the final temperature minus the initial temperature, right? T final minus the initial temperature. Now, as I'm heating it, I'm calculating the entropy as it heats up. So the temperature is increasing gradually. So what does delta T mean? In the limit, this one, if I'm increasing a little bit, if I'm increasing the temperature from, let's say, from T initial to T initial plus dt, from T initial to T initial plus dt, if I increase the temperature by a dt, by how much how much heat do I have to put? The amount of heat I would call it dq, and it is equal to mcw. This is delta T. So in the limit as delta T goes to 0, that's dt. That's what happens. In other words, it's just mc delta T, but instead of delta T, it's dt. So that, in other words, I don't have to wait for delta T to go from 0 all the way to 50. So every time the temperature increases by an amount dt, the entropy changes by a certain amount. So how much? So I have dq now. Here's dq, it's mcw for water, and then dt. So I go here and replace it. So I have mc water, and then dt, and then the 1 over t comes from this, right? There is a t here at the bottom. T. So now I have a function of just t. This inside only depends, the only thing changing is t. The mass is constant, the specific heat of water is constant. So, and we're integrating from a certain temperature to a certain temperature. We'll get to do that in a second. So I have the mass, Cw, the integral of 1 over t is always natural log of t. And so we're integrating from the initial temperature to the final. So it will be T final over T initial. And so now you substitute specific, the mass is 0.1. Specific heat of water, I think it's 4186 or so.
Yeah.
4186. And then the natural log of, again, temperatures, they must be in
Kelvins.
Okay, yeah. Otherwise, you'd be, in this case specifically, you'd be divided by 0. T final is 50 degrees Celsius, so that's 273 plus 50 273 plus 50 is 323. Okay. So 323. And then the 0 degrees Celsius is 273. And so you will get there. So if you multiply this, I will wait for you to give me a number.
70.4?
70?
Yeah, 0.4.
Thank you. So I will write it here, 70.4 joules per K. Sorry, I ran out of space. I should have planned better. But yeah.
What if it also changes phases? Would you add like Q, ML?
So we did this one, right?
Yeah.
So let's say you were given ice at 0 and it turns to water at 50.
Yeah.
So what you have to do is you first have to calculate the entropy change from ice at 0 to water at 0. And then you add to it the entropy of water at 0 to water at 50. So in that case, it would be 122 plus 70, so 192.
Yeah.
Thank you.
Yeah, welcome. And so, yeah.
So what would happen if you like theoretically reached absolute zero? Would the entropy just like be infinite or?
The third law would prevent that.
Okay.
Yes. You can reach absolute zero by a finite number of processes. The book doesn't even mention the third law of thermodynamics. So it basically tells you you can't get to zero. So, yeah, so we're safe. We're not divided by zero. Okay. If you're curious, I can refer you to something without a good discussion about absolute zero, if you want at some point. I don't know if anybody has the time because it's a busy semester, but at the end of the semester, you can remind me. I can refer you to something. Yeah. So that's what I wanted to discuss. And then the other thing I talked about was free expansion. So I want to just mention it. Yeah, just concerned about the time. The free expansion. You can expand. You can change the volume through different processes, right? You can increase the volume isothermally. You can increase it adiabatically. You can increase it by any other means, right? So if this is, here is the volume, here is the pressure. Let's say I'm here. This is V initial, and I want to increase the volume, V final. So I can just increase it this way, right? That's called isobaric. I can increase it isothermally. I can increase it adiabatically. But all of them will lead me to some V final. I can also increase it by just free expansion, suddenly. So what does that mean? Here is how it looks. And I just want to discuss conceptually what is free expansion. So I have a box here. This side of the box has a volume V, and this side also has a volume V. Now I have my gas molecules right here. So they have certain speeds, right? Certain speeds. I can increase, if this is a piston, I can remove it slowly this way. Let it slide slowly this way. In that case, I'm doing work, right? Doing work, probably negative work. Yeah, the gas is doing positive work. I'm pulling it, so I'm doing negative work. So, so that's one possible way. But what if I just break the barrier? How much work have I done? Let's say, or how much work has the gas done from the perspective of the gas? So if I just remove this barrier, suddenly, just remove it.
Zero.
Yeah, no work. The gas doesn't do any work. How much heat is entered if let's say the container is insulated?
No.
Zero. So if no heat has entered and no work was done, this is free expansion. So free expansion. So let me just twice V, right? So V and so here the molecules had a V to play in, to move in, but now they have twice 2V, right? The volume went from just this part to twice, so it's 2V now. And the molecules are this, seven. From here to here, free expansion. So I said zero work was done and zero heat was added. So what's the change in temperature? Will the temperature, right, the temperature here versus here, is it larger, smaller?
Smaller?
Or the,
I think it's
heard
smaller. Yeah. Smaller.
Okay.
Smaller.
How about, okay, thank you. I heard smaller. Does anybody think it's larger or maybe the same? How about that? Let's think about the kinetic energy of the molecules. Is it the same or no?
Yeah.
Oh no, it would increase, right? Because they have more space to move around.
There's more space,
So the
okay.
temperature might rise.
So let me write the first law. Delta E thermal, right? Is, what does the first law say?
Work plus Q.
Q plus W.
W plus Q. Okay. We said with free expansion, both are zero. W is equal to Q is zero. No heat is added, no work is done. So what's the change in thermal energy?
Zero.
Therefore, the change in thermal energy is zero. So the change in thermal energy is zero. So what do I conclude about the change in temperature?
Same.
It's the same.
Yeah, the temperature doesn't change, because remember the change in thermal energy is the NCV delta T? So if it's zero, the temperature is constant, temperature is constant, the change is zero. So, yeah, it will actually have the same temperature. I tell you why, intuitively, our intuition in this case, kind of tells us it should get cooler. Because if you have like a gas in a bottle and then you just let it expand, right, freely get out from the bottle, it cools, right? Why? What's the difference between them?
This is an insulated, an isolated system.
Yeah. So when it expands, when you let it in the environment, it's actually doing work against the environment. And this one, it's it's vacuum here. It's doing nothing. It's no work is done on it. No heat is added to it. So it is the same temperature. It would be the same temperature. Okay. Yes.
Does that mean the molecules are still moving at the same speed?
Yes. On average, yeah. Yeah. Yeah, due to time constraint, I was going to go into the calculation of the entropy change of this one when it's free expansion. How to do that? It's discussed in the book, but you might think the entropy change is zero. You might think the entropy change is zero because you would say temperature didn't change, no heat is added, so we should get zero change in entropy. But where's the flaw?
Volume.
The volume doubled, but there is kind of nothing here to tell me about the volume. Since the temperature didn't change, to get the entropy, I have to integrate this. It seems like isothermal. And I just integrate, I just get Q over T, but Q is zero. Look at the qualifier, entropy for what kind of process? Quasi-static process. Yeah. Reverse, basically a reversible process. This is how you calculate it. So this one, you cannot apply to the irreversible process to try to use this formula to calculate it. So the way it's done, the way you would calculate it is, you say, what I do is, the way it's calculated is, you say, since the temperature didn't change, and the volume doubled, I'm going to use a quasi-static process, such as an isothermal process, and I just double the volume that way. And since I started with 1V and I ended with 2V, and both of them led me at the same state, if it's the same state, remember entropy, volume, pressure, temperature, they're state variables. They're the same, during the same state, it's the same entropy and the same volume, the same pressure. It doesn't matter how you got to that state. And therefore, the entropy change in both cases would be the same. And that's how you would calculate it, but I'm running out of time, maybe during the discussion. Okay? So that's all I wanted to say, is to explain the term free expansion, in case you run into it. Okay? So again, what does free expansion do? Huh?
Irreversible.
It's irreversible. And what happens to the temperature in a free expansion?
So the same.
Stays the same. What happens to the average speed of the molecules? Okay, that's what I wanted to know. All right. And this leads me to chapter 21. Chapter 21, in a way, there is no new information. Everything there is to know that you will learn in chapter 21, you kind of already know. And so it's an applications chapter. Okay? So let me run through some terminology because I've got 30 minutes left. Some of it I will write, some of it I will not. And I'm trying to get to a problem, solve a problem about an engine. Yeah. So the first law is a law of conservation of energy, right? It says delta E thermal is Q plus W. To change the thermal energy, you have to do work, or you have to add heat. The second law talks about what processes can happen and which ones cannot. For example, you can spontaneously have heat flow from a cold object to a warm object. I'm sorry. What did I say? I said it the reverse. So that one cannot happen. You can have heat flow from high temperature to low temperature, but never the opposite way, spontaneously. You can do it, but it requires work to be done. Okay? So I mean, you can cool the room using a air conditioner or a refrigerator, right? You can cool it, make it even cooler. So you can transfer energy from a cool object to a hot object, but it requires work to be done. It's not spontaneous. So spontaneously, heat flows from high temperature to low temperature. Okay? So that's that. Now, we mentioned already in worksheet number 3 about the work done by the system and the work done on the system. So let me rewrite. The delta E thermal is Q plus W. By W here, what do we mean?
Work.
Work done by,
System.
That's why they.
No, done by the gas.
done on or by the system?
On.
On it. This is the work done on it,
So done by.
on the system. Now, that's fine. In this chapter, the author says, in practical engines, he wants to talk about the work done by the system. Because if you have an engine, you want to know the work it gives you, the work it does for you, not the work you do for it. They're the same up to a minus sign. So it looks like this. Delta E thermal is Q minus Ws. This is work done by the system. So they're just off by a minus sign. So W is equal to minus Ws, or Ws is equal to minus W. Okay. So if a gas is expanding, if the gas expands, the work done on the gas, is it positive or negative if the gas expands? So here's gas, here's the gas. It's here, and then it expands, becomes larger. So the volume has increased. The work done on the gas, is that positive or negative?
Negative.
That's negative, yeah. Imagine, here you are pushing this, but it expands. So your push is this way, but the motion is this way, so there's 180 degrees between you. So the work done by you, by the external thing, is negative. So when the gas expands, the work that you do is negative. The work done by the gas, on the other hand, is positive. Why? Because the gas is pushing, and then it gets to do what it wants to do. It makes the container larger. It pushes away the piston. So it's pushing this way, and the container goes that way. So the gas expands. So the work done by the system, by the gas, is positive. So when you do negative work, the gas does positive work. And when you do positive work, the gas will do negative work. Right? So there is a minus sign between them. Now, there is the term energy reservoir. So an energy reservoir is a large reservoir, and it's just labeled by a certain temperature. So for example, so energy reservoir. So it says it's an object or part of the environment that is so large that its temperature does not change. So here it is. So let's say there is a fire here. How do I draw fire? Yeah,
Just draw some squigglies.
like this?
Yeah, there you go.
All right, so here's fire. All right, it has a certain temperature, okay? Yeah. Yeah, sorry. That's why the book will have nicer pictures than the ones I can draw. Okay, so I can put a rod here. I can put a copper rod. So let's say this is a copper rod. So this is fire, and let's say this end of the copper rod is connected to an iceberg. Iceberg because it's large. So so heat will flow from the fire to the ice, right? This way. So this is called a hot reservoir, and this is a cold reservoir. Okay? So the temperature of the hot reservoir is TH, T hot or T high. And then the temperature of the cold reservoir is TC, so T cold. Okay? Does that make sense?
Yeah.
Okay. I mean, you might say, why am I doing this? Well, we're just getting the terminology out of the way. So when we say reservoir, that's what it is. And the copper rod is called the system, the thing that the heat flows through. Okay, so we draw what's called an energy diagram. The energy diagram looks like this. For this one, we usually say, here is the hot, T hot, okay? And then this is T cold, this is the cold reservoir, TC. And then heat will flow this way, right? That's the heat. It will flow from cold to hot. So that's one way. That's good. And the heat that flows from the hot reservoir is called QH. And the heat that arrives at the cold reservoir is called Q cold, QC. In this case, by conservation of energy, what do I know? What's the relationship between QH and QC in this case?
Equals 0.
Equal each other?
They're equal to each other, right? If you have 1 joule leaving this one, then 1 joule is entering this one. So in magnitude, they're equal to each other. Does that make sense?
Yeah.
Now, yeah. So usually though, what you want is, you want to heat something or use the high temperature here to give you some work. So it looks like this. What does do work for you mean? Well, we'll see. So you want heat to flow, here's QH to flow this way. And it does some work for you, W. It will give you some work output. And then the leftover heat gets dumped in here to the cold reservoir, Q cold. Okay. So what does work mean? So let's say this one is some boiler room. It boils gas into steam, and that steam, due to its pressure, it spins some turbine. And that turbine can generate, let's say, electricity for you. So that's the work it gives you. And then the steam doesn't just go away, it cools down a little bit because it gave you some work, but then it goes to some condenser, some cold reservoir, it gets cooled, and then recycled over again. It gets boiled and so on. So the work is whatever useful, it's called useful work because it's the work that you want. Okay? Does this make sense? Okay, good. So now, the second law of thermodynamics, you might say, why can't I get all this work all this heat to just give me work. Why can't this happen? So by the way, let me write this. This is possible. This is possible. But this is not possible. I'll show you what's not possible. Equal, this is QH to just give you work. You can't have this. You cannot just take all the heat from here and use it to make 100% work without wasting some energy. Okay? Wasting it as heat dumped into a cold reservoir. This one is not possible because of the second law of thermodynamics. And let me show you, first of all, is this clear what I'm trying to say?
Mhm.
Okay. The reason this is not possible is this. Since we're at it, so imagine it was possible. So it's called argue by contradiction, right? So you first assume, fine, you think it's true, let's assume it's true, and then we'll get a contradiction. So you will, let's say this is true. Well, I will connect it, this work, you can, let's say generates electricity for you, and you can run your AC, you can use it for your refrigerator, whatever it is. So let's say I'm running my AC. What does an AC do? It takes heat from a cold reservoir and then heats the hot, right? So let's say we're in the summer. It's already cold here, but your AC, what it does is it makes it even colder by removing heat from here and throwing it to a hot environment. How does it do it? Using electricity. Work has to be done by it, done on it. It can't be done spontaneously. Heat cannot flow from cold to hot, right? So if you want it to flow from cold to hot, you have to do work. It has to cost you. It doesn't happen spontaneously. So use this work. I'm going to show you why this cannot happen. So you can use this work to run your ACs. So let's say here is the work, and then here's the cold reservoir. And your AC, by doing work on it, it can remove heat from a cold reservoir and then throw the whole thing into a hot reservoir. So if this were to be true, I can use it to run my AC. But look at the net thing that's happening here. What's happening here? So from the hot reservoir, we're taking QH, right? But here, what's going into the hot reservoir here?
Working.
It's QC plus W. Yeah, by conservation of energy. Work is in, QC is in, so you have to throw QC plus H this way, right? This is W plus this. So this will be W plus QC. But what is W? I'm using the whole heat. I'm using QH. So W is actually equal to QH. So this is equal to QH plus QC. But look at the net effect. I take QH from the hot reservoir and I give it QH plus C. So what's the net effect? What's the net effect?
W.
Yeah, I'm taking QC from the cold and adding it to the hot spontaneously, because I can draw a box around this, and this will just be an isolated system by itself, and this isolated system can run forever and just keeps giving me takes heat from the cold to the hot. Okay. We'll get to this argument more when we show, and that's not allowed. The whole argument is this: since the net effect is just you're having QC spontaneously flowing from here to here, that's not allowed. Okay? And so we'll get to that. Maybe I mentioned it prematurely because it's toward the second half of the chapter. That's when they talk about it. But I wanted to say that this is not possible. This is not possible. You have to waste heat. Okay, let's see. So what's possible, what is not possible. Now, efficiency. What is the efficiency of an engine? So, let's say you have your car engine. You burn fuel, right? If it's not an electric car. So you burn fuel, and then when you burn fuel, you get your car to run. But then your exhaust would throw some heat to the outside environment. So the work done, the efficiency of that engine, of the car engine, or whatever the engine is, will be how much work you get versus how much fuel you have burned, right? So the efficiency will be this. Efficiency. Of a heat engine. So it looks like this. It is given the name eta. It's a Greek letter. Eta. And it is the amount of work that you get, the work that you get out of the engine, versus the amount of heat that was burned to give you this work. So you took heat, let's say you burned fuel, and you got a W out. So how much, what is the efficiency? Well, if you burn 100 calories of fuel and you only get 20 calories of work, your efficiency would be 20%. So W over QH. Another way to write this is sometimes written as, because W plus QC, right, this one, I drew it diagonally this way. Let me draw the QC, write the QC again. What do I know about QH, W, and QC by conservation of energy?
QH equals to QC plus W.
Yeah, QH, the energy in has to equal to the energy out. The energy out is W and QC. So W plus QC is equal to QH. So I know that W plus QC is equal to QH. That means W will equal to QH minus QC, right? Mm-hmm. And you can substitute that here. So QH minus QC over QH. And this fraction can be simplified because QH over QH is what? 1. And then minus QC over QH. And so the efficiency basically can never be 100%. Far less, in fact. It's usually, it's 1 minus something. 100% means 1. Yeah. Conservation of energy says nothing about that being forbidden, that this process cannot happen. This perfectly does not violate conservation of energy, but it violates the second law of thermodynamics. So the second law prevents 100% efficiency. And the efficiency, usually it says here, actual car engines have an efficiency of about 10 to 50%. So, 10 to 50%. Not that much. Yeah. And it's not technologically advanced or anything. But the second law of thermodynamics just can't. You can't.